I've always been fascinated by rockets. These massive vehicles are one of mankind's greatest feats. Rockets can accelerate fast enough to escape Earth's gravity and travel to distant places such as the moon. How is this possible? How can a rocket generate enough acceleration to launch such a huge object? I had a lot of curiosity about these questions. It turns out that the chemistry of rocket fuel is the answer. The general concept of rocket fuel is relatively simple. It's not rocket science. Well, I guess it is rocket science, but it's still pretty simple. Rockets contain a propellant, also called a fuel, and an oxidizer. The propellant and the oxidizer are exposed to heat. This causes them to undergo a combustion reaction. The product or products of this reaction are gases. Since these gases are so much less dense than the solid or liquid reactants, a high pressure is developed. This high pressure causes the gases to leave the rocket, pushing the rocket up. Liquid oxygen is the most common oxidizer, but many different propellants are used in different rockets. I will examine the propellants used in the Saturn V rocket, the rocket that went to the moon. On the SIC stage of the rocket, or the stage at the bottom of the rocket used for liftoff, 318,000 gallons of liquid oxygen were used as an oxidizer, and 203,400 gallons of kerosene fuel were used as a propellant. On the S2 stage, or the next stage closest to the bottom of the rocket, 80,000 gallons of liquid oxygen were used as an oxidizer, and 260,000 gallons of liquid hydrogen were used. On the SIVB stage, the stage furthest from the bottom of the rocket, 19,359 gallons of liquid oxygen were used as an oxidizer, and 66,770 gallons of liquid hydrogen were used as a propellant. In the reaction between liquid hydrogen and liquid oxygen, the reaction equation is 2 liquid hydrogen molecules and 1 liquid oxygen molecule with heat as a catalyst yield 1 gaseous water molecule. This reaction can generate heat up to 5,500 degrees Fahrenheit. The reaction in the video was very similar to the reaction between liquid hydrogen and liquid oxygen, except that hydrogen and oxygen were gas in the video. Hydrogen needs to be stored at negative 423 degrees Fahrenheit, and liquid oxygen becomes liquid at negative 297 degrees Fahrenheit. The exact reaction between kerosene fuel and liquid oxygen is unavailable because the kerosene fuel used by NASA, called RP1, has a military classification on its chemical formula. Most kerosene is a mixture of hydrocarbons containing 10 to 16 carbon atoms per molecule and 22 to 34 hydrogen atoms per molecule. Each of the hydrocarbons react with the liquid oxygen. This hydrocarbon is pentadecane, C15H32. This reaction between pentadecane and liquid oxygen is 1 liquid pentadecane molecule plus 23 liquid oxygen molecules with heat as a catalyst yields 15 gaseous carbon dioxide molecules and 16 gaseous water molecules. All of the reactions using the hydrocarbons from kerosene use different amounts of liquid oxygen and produce different amounts of carbon dioxide and water. Some reasons why these different fuels are used are because of their storability, specific impulse, and density. Kerosene is much easier stored than liquid hydrogen. Since liquid hydrogen needs to be stored at negative 423 degrees Fahrenheit, this must be insulated extremely well from the heat generated from engine exhaust, air friction, or the sun. Liquid hydrogen has a much higher specific impulse, or ISP, than kerosene. Specific impulse is basically how much thrust different fuels produce with the same amount of fuel. In a vacuum, liquid hydrogen has a specific impulse of 455.9, and RP1, or kerosene, has a specific impulse of 354.6. Liquid hydrogen has about a 28.5% higher specific impulse than kerosene. This means hydrogen powers the rocket much more efficiently than kerosene. Kerosene has a higher density than liquid hydrogen, however. Hydrogen has a density of 70 kilograms per cubic meter, whereas kerosene has a density of 820 kilograms per cubic meter. This means hydrogen is a much bulkier fuel than kerosene, requiring more materials to store it for the same amount of weight. This added material adds a large amount of weight and requires more thrust to be able to lift off. Since so much fuel is needed for the first stage, this added bulk would make liftoff very challenging. Thus, kerosene is used. On the upper stages, not a great amount of fuel is needed since the force of gravity is not as strong further away from the Earth, and the air resistance is much lower. Since hydrogen's bulk is not as important, its higher specific impulse is an advantage on the upper stages. While hydrogen is so difficult to store, its high specific impulse still causes it to be used over other rocket fuels. Without the chemistry of rocket fuels, rockets would be impossible, and many incredible feats, such as walking on the moon, would never have happened. Thanks for watching.